Hello everyone, Gülzar Zey here. I'm a postdoc at Princeton. I broadly work on biomolecules and the role of water in biomolecular assemblies. But here, I'll just focus on pure water. Something makes water so special that it's the fluid of life. Many of the physical properties of water are fundamentally different from those of most other substances. For example, ice floats in water, exemplifying volumetric anomalies of water. But it is not just that. Thermodynamic response functions of water, such as isothermal compressibility and heat capacity, also show abnormal behavior, which becomes more pronounced as water becomes supercooled. So, what is going on? One possible explanation to water's anomalies is that the supercooled water is approaching to a critical point. According to the critical point hypothesis, there is a pressure where the response functions diverge as temperature decreases. This pressure would be the critical pressure, and the temperature at which the response functions diverge would be the critical temperature. Together as a state point, Tc and Pc would be the point of singularity, in other words, the critical point, the second critical point. This hypothesis, however, is very hard to justify or falsify because this hypothetical divergence happens at deeply supercooled conditions where ice nucleates too fast. So this is the reason why molecular simulations are extremely important in this field. So what did we do? We did simulations of pure water systems near their hypothesized critical point using two realistic classical models of water. We rigorously analyze them using two independent techniques, one of which is exactly as in scattering experiments, and the other one is the modern theory of critical phenomena, where we drive the order parameter that shows the phase symmetry at the critical point. In both techniques, we compared our system's behavior with that of icing model at its well-known criticality. And for the first time, we unambiguously showed that a second critical point indeed exists in two realistic classical models of water. And this criticality belongs to icing universality. Related to implications, we need to talk about what happens beyond this critical point. Critical points mark termination of phase coexistence curves. So what are those phases for this case? According to the computational findings, this critical point terminates the coexistence of a high-density liquid and a low-density liquid. And effects of critical points can be felt far away from the point itself, so it would even impact the water at ambient conditions. And anomalies of water possibly arise as a result of the existence of such a critical point. Now, before closing, I again note that these arguments rely purely on computational findings. Although there is a lot of experimental evidence supporting this, there isn't yet any rigorous experimental proof of such a critical point. Thank you for listening.